what are we doing here? This is fantastic. This is a levitating frog. So how do you levitate a frog? It's got to be something to do with what we're talking about, right? It's a really strong magnetic field. It's like 10 to 12 Tesla, something like that. So typically when we think of magnetic materials, we think of things like iron rods or something like that. We all have a little bit of a possibility of being magnetic. This is something called diamagnetism. It's the paramagnetism, like what we see in iron rods, or ferromagnetism. We all have water in our bodies. The electrons in water have some spin. If we put those in a strong enough magnetic field, they're going to align, and you have what you see here, which is the floating frog. Yes, in theory, we could do this with a person, but oh, that's a strong magnetic field. Somebody won a prize for this. I'll tell you more about this later down the road, just to break up the material a little bit. All right, that's not what I wanted to do. I got distracted. Anyway, back to what I'm supposed to be talking about, which is this stuff right here. So as I said, sections 20.1 through 20.3, and then 21.3. We're talking about electromagnetic induction and transformers in these sections. And I played you the Andre Geim video down there at the bottom of the page. That was the floating frog. I'll hopefully come back and talk about some of these other links in the next couple lectures. Okay. All right. First, I want to give us a little motivation for why we're studying this material. It has to do with power generation. An example of that is on the left-hand side here, where we see the windmills. Generation of our electromagnetic power fundamentally relies on electromagnetic induction, and we'll talk about what induction is in just a minute. In addition, with the concepts of electromagnetic induction, we can generate a current in a person's brain, and then we can image that current. As we can see on the right-hand side, there are areas in red are where the currents are strongest, and then based on that information, that can tell us something about the brain. We can also, this is transcranial magnetic stimulation as a therapeutic tool. Yes, that's exactly what I wanted to talk about. We can use this idea to actually treat some types of mental illness. So rather than electroshock therapy, or I don't want to say or medication, I'm sure it's in addition to medication. This idea of putting currents in the brain can be used to treat some forms of mental illness. Electroshock therapy was done for that in the past. It probably is still done, but electroshock therapy is a brutal technique, whereas this is much more refined. All right. Anyway, electromagnetic induction, what is it? Well, as we saw in our lab that is due today, that many of you have already done, but some of you probably are still working on, a changing magnetic field can be used to generate an electric current. And this is exactly what we did in that simulation. We brought a magnet near a coil of wire, and we pulled a magnet back. We flipped its poles around. So on and so forth. But what did we see as we brought that magnet near that coil? Well, as long as we were moving it, we saw that the needle on our voltmeter, or the needle on our current meter, whichever one we're using, was deflected. In the middle panel, we see that the needle is deflected to the right. So maybe we've got we'll call that positive current running in one direction. And then when we pull the magnet back, we've got current running in the opposite direction. So what causes this? Well, it's the changing magnetic field that produces the current. So as we bring the magnet closer to and further away from the coil, we're changing the field strength through that coil. And as we change the field strength through the coil, we're inducing a current. Okay, and that's exactly what this slide says, that this current that we're causing is what's called an induced current. It's an induced current that's caused by a changing magnetic field. Right. So changing a magnetic field can cause an induced current depending on if the geometry of whatever apparatus we're using is right. Okay. So if there's a current, then there's got to be a voltage driving that current. This voltage, we're going to use the old archaic term EMF for it, electromotive force, which isn't really a force, but whatever, EMF. EMF and voltage are interchangeable. But this induced voltage, we're going to call an induced EMF. Okay. So changing the magnetic field through the coil causes an induced EMF. All right. One other geometry we can have is, well, say we've got some magnetic field in the region of space, and then we've got some circular coil. Some circular coil. Okay, you guys can see the circle I'm making in front of my face, hopefully. And we've got a magnetic field through it. Well, when we change the shape of that coil, we change the number of field lines that penetrate through that coil, because we're changing the area of the coil, so we're changing the amount of field that can pass through it. And this can also generate an induced EMF and a current in the coil. So producing an induced EMF is a process called electromagnetic induction. All right. So we're going to look at another way that we can produce an EMF besides just this coil that we've talked about, changing the magnetic field near the coil or changing the magnetic field through a coil by changing its area. We're going to look at what happens when we have maybe and I changed my mind about which tool I want to use. We're going to look at what happens when we've got, hello? Okay. When we've got, say, a metal rod, and it's moving that away to the right. And this metal rod is in a region of space where there is a magnetic field that is into the page. All right. So there's a magnetic field into the page. So I want you guys to picture something. I want you to picture maybe an electron hanging out right around there. It's a metal rod. Metal would be a conductor. That means we've got electrons that are free to move around. We've got this electron. I did kind of a lousy job of, let me fix that. I'm not going to be able to live with myself right now. I've got a number of people right now in my house that probably feel the same way about living with myself. But see, that was a joke. Just anyway, we've got an electron that's moving to the right, and what's going to happen? Well, why is it moving to the right? Because it's inside the rod, and the rod's moving to the right. Okay. What's going to happen to that electron? Well, you tell me. Now I feel like Dora. Anyway, what's going to happen is it's going to experience a force. We've got a moving charge in a magnetic field, so it experiences a force. Which way is that force? Well, I'm going to, again, do this with the right-hand rule. My fingers point in the direction of the charge is moving in. The palm of my hand is pointed away from me. Which is the direction of the magnetic field is away from me, is basically into the screen, which I am looking at the screen. So my palm is facing the screen. And then, yes, okay, my fingers can curl in that direction towards the screen. So the force on this charge would be upwards, right? Well, it would be, except for the fact that it's an electron and everything gets flipped. So as a result, there is a what? There's a force downwards here. And then, so what happens? Well, we have some electrons that basically end up moving down here to the bottom. And where are they moving from? Well, I know I drew it as being in the middle, but what's actually going to happen is they're going to end up migrating from this region up here at the top. So we've got a separation of charge there. We've got a positive, you know, if we could picture, if we could imagine that there are positive charges that are free to move, they would accumulate up at the top of the rod. Negative charges would accumulate at the bottom. You know, what's actually going on? Well, electrons from the top are moving down to the bottom and leaving an excess of positive charge up at the top. So we've got separation of charge there. We've got a positive charge and a negative charge separated by some distance of space. Say the length of the rod is capital L, whatever. So they're separated by L. So can you guys think of another situation where we've got charge separated? Where something's got a positive side and a negative side? Batteries. Yeah, a battery. So what we could actually do, and this is kind of cool, is we could take this rod that's moving to the right in this magnetic field, and we could put it on top of a couple conducting rails, or maybe drill holes through the rod and then slide it onto the conducting rails and move that rod to the right. And if we had maybe a light bulb or something like that, we could actually end up driving a current through that light bulb. Why? Because, well, we've got positive charge right there. We've got negative charge right there. And what's going to happen? We're going to have basically charge go from the positive side around there to the negative side. We've got a current. That's the direction of my conventional current. Yeah, hopefully you guys get it. This is what this process is called, again, creating an induced EMF. Specifically, this is what's called a motional EMF. All right. So we haven't done any calculations yet. That's coming. That'll be coming in the next video. So I will talk to you guys some more in just a minute.